It's time now to move on to trigonometry, and today we're going to look at the unit circle. First of all, let's recap some basic right-angled trigonometry. So in this case, I'm dealing with a right-angled triangle where I know the hypotenuse, and I want to find the opposite side. Well, if I know the hypotenuse and I'm looking for the opposite, the ratio I should be using is that sine of theta is equal to the opposite side divided by the hypotenuse. In this triangle, I know that the hypotenuse is given as 1, so this becomes the opposite side divided by 1. Well, when I divide something by 1, it doesn't change, so the opposite side is sine theta. So the height of this side is going to be sine of theta. I can apply exactly the same argument here when thinking about the base of my triangle. This time, I know I've got the hypotenuse and I've got the adjacent side. This time the ratio that I'm using is that cosine of theta is equal to the adjacent side divided by the hypotenuse. Again, the adjacent side divided by 1, so I have just the adjacent side. So cosine of theta is equal to the adjacent side. So this length here becomes cosine of theta. Now it's really important to emphasize here that this is when we are talking about the hypotenuse being 1. Now the title of this video was about the unit circle, because that's what we want to look at now. This is a circle of radius 1. The reason that this is so important to us is because, as we've just seen, if I form a triangle where the hypotenuse is 1, I know that the height of my triangle is going to be given by sine of theta. And I know that the base of my triangle is going to be given by cosine of theta. Or in this case, we know the angle, so this would be sine of 60, and this would be cosine of 60. So here I have a setup in Geogebra, the link for which I'll put in the description for this video. It's animated, so I can run my unit circle with the angle ever increasing around. Now, as we've just talked about, if I want to find sine of my angle, that's simply the height at that point above the x-axis, or its height below the x-axis. Now let's get on to thinking about how we might plot a graph of this. Well, we know its height, so let's just put on a line that's going to show there the height of that sine graph. Now I just need to plot the x values, like so that at any given point, and if we stop just here, I know that when x is 136, so if I measure from here 0 to 136, the height of my graph is going to be sine of theta, which is here. Which just so happens to have the same value as something else over here, which we'll talk about more in the next video. But this is where our sine graph is generated from. As we increase the angle, we look at its height above the x-axis or its depth below the x-axis, and that's how we generate our sine graph. Now let's start thinking about cosine. So cosine was then going to be the bottom part of our triangle. We can do exactly the same thing, where we start thinking about plotting this graph, this time, with its width in comparison to the x-axis. And again, if I start plotting my point, so I'm going to wait until this comes back round to 0, and plot from 0, this time down my page so that it fits on nicely. As the angle increases, we can see how this matches up perfectly with the cosine line that we had on our unit circle. And this is where these two functions come from. So we have our sine graph drawn up here, and our cosine graph drawn down this way. Now, obviously we wouldn't ever see it in the cosine graph in this format, we would always rotate it round, but we'll talk about that more again in a different video.